Okay. So let's start from where we gave up. Finished in the last class. We had basically defined the collision, where we say that particles are approaching each other with V1 and well, V1 and V2. And that could be written in terms of the center of mass frame, where the two particles are approaching along exactly opposite each other, but with different velocities, mu by m1v capital and mu by m2v capital, plus and minus signs. And our aim is to have some simple expressions for the scattering cross section. So that's where we are heading for. So now what we're going to do is discuss that the scattering cross section is going to be invariant under time reversal, which you shall uh, understand rather easily, but also it is going to be invariant under space inversion. So our focus is the inverse collision, so the forward collision and the inverse collision, because the reason you will see soon. Let me not. So when you have uh, scattering, so let's look at a picture. So suppose this was the original collision. So some particles were coming with relative velocity v, and it was scattering into some relative velocity v dash, right? So two particles are, so we are just plotting the relative velocity capital V with respect to each other. Of course, the two particles have two different velocities, V1 and V2, and after scattering they have V1 dash and V2 dash. But if you are moving with the center of mass frame, we are just plotting the relative velocities that they are coming at V and then going off with V dash. Now, if there was a time inversion, if the time went from t to minus t, then all the velocities would be reversed. So V1, V2, so basically, so when the scattering is happening with the forward time, so V1, V2 was going to V1 dash and V2 dash. So if under time reversal, it will basically come back. So it will just retrace its path. So the relative velocity will be v dash, and they're going to go out with velocity v, because each path is retracing its previous path, right? The force would remain intact, right? Force is not, if it's a function, it's an r dependent force, so that doesn't change, but the velocities, the direction of forces is that m d2r dt2 is equal to fr remains intact, because t goes to minus t. There is a double, I mean, there's 2 times a derivative, thereby the equations of motion remains unchanged, right? But all the particles are going to retrace its path. That's what the time reversal or the reverse collision. So if some particles are coming like this, they're going to go out under the same kind of interaction, the opposite direction. The equations of motions are invariant under time reversal. But the point is that the equations of motions are also, I mean, just let's discuss the equation of motion also are also going to remain invariant under space reversal, and then it's called the inverse collision. So in inverse collision, what you're doing is r is going to minus r. Okay, the time remains, the t is always it's going in forward direction, but the time, but the space is going from r to minus r. So if there's a force acting in a particular direction, plus r, it also goes to minus r. Now that seems a bit non-intuitive. So I have so suppose there was a particle which was doing a SHM, simple harmonic motion, about the origin. For whatever reason, it's doing a simple harmonic motion along the origin. This was distance x, right? So it would go from here to here. So it's suppose that we are observing at a certain point of time. Okay, t0, and at time t0, it was at this position and moving in this direction towards the center, right? And thereafter it would go like this, and so on and so forth. This is how it would do its SSM. Now suppose under space inversion at time t0, if you suddenly invert the space, this position would go to this position. Under space inversion, this would go here. The velocity which was moving in this direction would go in this direction, right? And now what happens is, as time goes forward, it is going to move in this direction and reach here, and thereafter go like this, and so on and so forth. So if this was the point which we were looking about, so under inverse collision, not inverse collision, this is just I'm trying to explain what space inversion means. So all r goes to minus r, the direction of force reverses, and now this particle after space inversion starts moving in this direction. Now if there was a collision, right, if there was a collision, what would happen is, so v1 v so here what happened, it all the particles after was starting to retrace its path back, right? But as a consequence of space inversion, you would have something called a inverse collision. In that, the particle will still move forward, but if it was going with velocity v, so it was going with velocity v and then coming out with velocity v dash. Now what would happen is you have inverted v dash, I mean the space coordinate. So everything will happen in the opposite, so that this would go in v dash and emanate out, and as it would go ahead in time, it would go with velocity v, right? So that's the consequence of inverse collision. So v1 v2 was going into v1 dash v2 dash. On the other hand, as a consequence of space inversion, the equations of motion remain invariant, and as a consequence, v1 dash v2 dash after interaction would emanate out as v1 and v2. So this is the primary difference. So here it was v1 dash and it was going out like this, whereas here this is going ahead in time. If anything was interacting with v dash, would come out under the same scattering cross section with velocity v. Now the details. Okay, so why are we doing this? So the reason we are doing it is, what we want to figure out is, under the effect of collisions, how are FRVT affected? So if due to let me give you a physical picture of what this FRVT and how does it get affected. What does that mean? So suppose this was so this is coordinate r, and so we have discretized space, so that at different points in r, at these red spots, you have an f of v defined. What does f of v mean? That how many particles are going at a particular velocity v at this position at a particular time. Okay. So now, so just to think about it, suppose at this point, so you have an f of v defined at this point, this point, this point, and this point. So we have discretized space, and let's just think about that we have discretized velocity also. So there's a certain number of particles. So suppose the velocities are v1, v2, v3, v4, v5, v6, v7, and v8. So we have just 8 velocities in a 2D in a 2D space. Then f1 v1 is the number of particles having velocity v1 at position r. f2 v2 is the number of particles with having velocity v2 at position r at a certain time t. So f is also a non-equilibrium, and here we are not considering equilibrium, so it could have deviations from the equilibrium. In fact, that's what we are trying to figure out, how would a system relax towards equilibrium. And similarly, fv3 is the number of particles which are moving with the velocity v3 at r3. Now, due to the collision between particles, the number of particles which were going with velocity v1, some of them would be scattered such that they would have velocity v2. So fv2 would increase because of collisions of particles. Suppose particles which are moving with velocity v1, the number is fv1. They are colliding with some particles with velocity v8 with a certain scattering cross section such that the number of particles moving with velocity v2 is increasing. So some particles which were moving with v1 are going and having, after the collision, velocity v2. Some particles which had velocity v1 after collision with v8 could also end up with having velocity v3. So again, fv1 is decreasing and fv3 is increasing. But the inverse collision could also happen in that some particles which have velocity v3, they on colliding with, say, v6 are, depending upon the scattering cross section, they could start moving with velocity v1. So fv3 would decrease, and due to collisions, they are incident on the particles which have velocity v6, and after scattering, some of them are going into v1, and some of them, just as an example, might be, of course, they conserve momentum and energy and all that, are going into v8. So that's also possible, right? So, but so the point is, we have to figure out in the forward collision that how many of these particles moving with velocity v1 and colliding with v2, v8, v7, v6, v5, and v4 are going and increasing the number of particles moving with velocity v3, and conversely, how many of v3 colliding with particles who are moving with v8, v7, v6, v5, v4, v2 are going and increasing the number of particles moving with velocity v1. So we have to consider both, because at the moment what we are due to collisions of particles moving with v1, they are going out of, they are changing their velocity. On the other hand, other particles which have different velocities as a consequence of collision are increasing the number of particles which are with velocity v1. So this is what is happening, and this is happening at each point in space. Hence, at each point in space, each value of frvt are going to change. So remember, at each point in space, and f for each value of v at each time, they're going to keep on changing, and the system is going to evolve. So that's the role of the Boltzmann equation. Now, it is to be remembered that for the scattering cross section, it is not only this scattering cross section actually microscopically depends upon the distance between the two center of masses as they approach each other, right? So that's a microscopic quantity, and it is also going to depend upon the various forms of the interaction and the various forms of the potential and so on and so forth. So basically, sigma is not only dependent upon the nature of the interaction, the equations of motion, and the so-called impact parameter, which basically is, I mean, if you consider one of the particles fixed, like you move to the frame of reference, which is moving with the velocity of particle 2. So in that frame, the particle 2 is fixed, it's not moving. This particle is moving and approaching each other at a distance at an impact parameter of b, which is the distance between the centers at the position of minimum approach, right? The perpendicular distance. And so it's the point where this distance becomes the minima, and thereafter it keeps increasing. So with this background, so all this sigma is going to depend upon that. But and that's why, depending upon the problem that is in question, and depending upon the distances, you have to have a more complicated you're going to have more complicated expression for the collision function. But to try to get it to a simple form, we are with this discussion of collisions, let's move ahead in getting an expression for the Boltzmann equation, the collision term of the Boltzmann equation. On the other hand, so basically the right hand side of the Boltzmann equation, dc, which we previously used the single relaxation time approximation. To go further, what we are going to assume that you have a dilute gas, so that we can have to consider only two particle collisions. What we are also further assuming that FRVT itself doesn't vary over the time of the collision. So the time of the collisions is much smaller than the time scale of evolution of FRVT. So there is a large number of collisions. So each of the FRVT has due to which, so these collisions happen at extremely small time scales in nanoseconds or 10 to the minus 10 seconds. On the other hand, we are really looking at the evolution of FRVT at much larger time scales, say microseconds or something like that. And furthermore, we are assuming that the mean free path, the average, the distance over which the particles move before they undergo a collision, is much larger than the range of interaction RC. So you are assuming that the particles which are had a collision, they are moving in straight lines, and for a very short time they interact, have a scattering cross section, due to which they move to V and V dash, right? So this last assumption is called the assumption of molecular chaos, and a consequence of which is that one considers that the incident velocities of the two particles are uncorrelated. If they were interacting, even as they were approaching each other from large distances, right, then their velocities, I mean, then that would mean that even after, just after their previous collision, the velocities are going to be correlated, in which the two particles are going to continuously see each other and change its path of collision. But we are going to say, the okay, it had some collision with some other particles, then they are moving with velocity v1 and v2, coming for a quick collision, and then dissipating away with velocity v1 dash and v2 dash, right? So the incident of velocity of two particles are uncorrelated, and for that you need the assumption of molecular chaos, which says that the mean free path is much greater than the range of interaction, the range of the potential RC, right? So with this, we slowly come to the final slide, or maybe not the final, yeah. So with this background, what we are trying to say that the DC collision of FRVT has a term which leads to the decrease of FRVT. So there are collisions such that the number of particles which were moving with, suppose, velocity v1 are going and are after collision having velocity v2, v3, v4, v5, v6, v7, which means the values of f of v2, fv3, fv4, fv5, fv6 are increasing. On the other hand, in the inverse collision, because of inverse collision, there are going to be collisions between v2 and v3 and so on and so forth. I mean, sorry, the number of particles with velocity v2 and number of particles velocity v3 is a consequence of which f v3 and fv2, of course you have to consider energy and momentum conservation, but this I'm giving the picture, are going to decrease, and that is going to result some of the particles which had these velocities, they start moving with velocity v1, as a consequence of which f v1 at position r at time t is going to increase. So the effect of collision will be the sum. So this is due to collisions, f of v1 is decreasing, minus sign, and this dc plus is due to collisions, the value of f1 at r at t is going to change. So for every value v1, v1, v2, you are going to have a negative term, so that particles which are moving with velocity v2 are going off and occupy and taking some other velocity, a consequence of which of f of v2 at r is going to decrease, and this term is other particles which are moving with other velocities as a consequence of collision are going to have velocity v2, say, previously we was giving the example of v1, v2 say, and hence f of v2 is going to change at position r. This same thing is going to happen at different points in r and at different points in time, and the details will really depend upon how quickly the thing will reach equilibrium, will really depend upon the scattering cross section, which in turn will depend upon b and the range of the interaction. But even for any range of it, for any particular interaction, classical, we can consider the ideas of forward collision and inverse collision, in that particles which were moving with v dash are going to v1 dash and v2 dash are going to occupy velocities v1 and v2, or the relative velocity is, or talking in terms of relative velocities, suppose this was 1.1 particle was approaching with relative velocity v dash and goes off to v. So that's the picture we are having. This is the inverse collision, this is the original collision. So to write that down, what we have to do is dc minus this one f. So basically the number of particles moving with velocity v and v plus dv vector within position within a volume d3r. So you say that, okay, so this is d3r, how many particles are within d3r in this region at position r, and how many are moving with velocity v1 and v plus dv1. Here we have discretized it, hence you don't have dv1. right? Here you will have velocity of v1. But in general, if it's a 3D space, how many particles are moving with velocity v and v plus dv vector? And that depends upon the number of particles. So here you are saying how many leaves. So what? So particles which are moving with velocity v1, how many leaves that and get velocities v2, v3, v4, v5. So that depends upon the number of particles moving with velocity v in d3r, and so Fv is the number of particles moving with velocity v in d3r, and they are incident. So number of particles velocity v, they are incident, or they are colliding with velocity with particles moving with velocity v1. And how many particles are moving with velocity v1? Fv1 into d3v1. You could correspondingly think that the number of particles moving with velocity v1 in this figure, they are colliding with velocity with particles with velocity v2. They are colliding with velocity v3. The number of particles moving with velocity v1 are colliding with velocity v4, right? But whether they will really collide or not, that will depend upon their relative velocity, right? So you are essentially integrating. So f v, these particles are incident on velocity, different values of on particles moving with different values of velocity. Hence there's an integration over v1, all the different values of velocity. So there's an integration over v1. This is the relative velocity, because v is incident on v1, and they're going to meet only if the relative velocity is appropriate, but you're integrating over 1, and this scattering cross section is going to depend upon v1, right? And they are scattering out into v2, v1 dash and v2 dash. So v on incident over v1, so the number of particles with velocity v colliding with all sorts of velocities v1 integrated over v1 are going to occupy all possible, they could, the particles moving with velocity v1 on colliding with particles with velocity v2, depending upon the scattering cross section, could go and have velocities v3, v4, v5, v6, v7, right? All possible things. And on collision with this and this, what velocity it will occupy will depend upon the scattering cross section. So that is what is being said. So here we are really looking at the decrease of Fv. We are integrating over v1 and all the possibilities of v1 dash and v2 dash that are possible, and how many are going to go into v1 dash and how many are going to go into v2 dash, whether at all it will go or not is going to depend upon sigma dash, right? Similarly, just the inverse, and since equations of motion remain unchanged, if particles were moving with velocity v1 dash and v2 dash on collision, so v1 dash collision with v2 dash, some of them are going to have an inverse collision velocity v1, and some are going to have velocity v. We are interested in how is f r Vt changing, and all possible combinations of v1 dash and v2 dash. So there's an integration over v1 dash and v2 dash, and also it could result, depending upon the scattering cross section, on different values of v1, as long as they contribute to change velocity or v. You are basically integrating again over v1 dash, v2 dash, and v1. And at the end, this is going to contribute to a positive and increase in the value of f rvt. They are going to increase the number of particles moving at our velocity v at time t. So and this, because the equation of motion are invariant, v1 dash, v2 dash going to v1 and v2, and all possible combinations. But if you choose a particular value, then this and this are going to be equal, because equations of motion remain invariant. So this scattering cross section is going to remain invariant, as a consequence of which we can write df. Df was the left hand side of the equation. It was del f del t plus v dot del f del r plus f by m del f del v equal to dc, the effect of collisions, how collisions change. So this was due to flow in explicit dependence of time, a dependence on space, a dependence on velocity because it's moving in a six dimensional space, right? So this is without collision. So f, the particles will keep moving with the same velocity and so on and so forth. And if there were other particles coming in, that would change del f del r, that could change as a function of space. There is other f's coming, so that could change. But due to collisions, the effect would be integral over v1, v1 dash, v2 dash, and we are looking at the effective change of fv. fv1, so this was leading to a decrease. This is to an increase. This is the scattering cross section, which remains the same for identical combinations of v1 dash, v2 dash, and v1, and of course v. And this is the relative velocity, because so many particles. So so here it means that v. So here basically particles with velocity v were incident on particles with velocity v1, and here v1 dash are being incident on v2 dash, but the relative velocities remain unchanged before and after the collision, right? So hence you have this relative velocity sitting here, and this is the Boltzmann equation incorporating collision and correlations, and this is Rife equation 14.3.8. I'm pretty sure you have to refer Rife to it because this is a difficult concept, and this is going to be the starting point uh, for future calculations in astronomy, in condensed matter physics, in statistical physics, and fluid mechanics, or whatever be, because this is how particles due to collision are going to uh, approach equilibrium, or if there is a driving, if there is an F by M, then you have more detailed expression depending upon your scattering cross section, what will be the relaxation, or how is FV going to evolve. And if you have FV at different points in space and time, then from that you can calculate other locally, you can basically integrate over the whatever quantity you are interested in and calculate that as a function of space and time at scales much larger than the collision. So here, of course, each of your volume had a large number of particles. So you can say that, oh, temperature is varying, I have average kinetic energy, because of these interactions are changing as a function of space and time, or the momenta of these set of particles are changing as a function of space and time. So you're going to integrate momenta of the individual particles over F, R, V, T, and do so on and so forth. And these need not be uniform over space and time. So this Boltzmann transport equation is going to be the beginning of other calculations in more advanced courses. But with this, we have just stated the collision term. We are not going to do any further calculations with this. With this, we'll end this part of the Boltzmann module. Anything more? No, this was just to explain. Yeah, fine. I think this is. So yeah, so this was this opposite momentum discussion. Basically, the two particles approach each other with. Okay, so now how do I stop recording?